Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today, we are taking a deep dive into the representation of AC current and voltage by rotating vectors phasors. It's a crucial part of Unit 7 alternating current. And our mission, as always, is to make this complex mathematical tool simple, visual, and, completely exam safe for you. So let's start with a practical problem. You see the sinusoidal waves for voltage and current, they are continuously changing, right?
Yes, moving up and down, 50 times a second.
Exactly. Now, picture this. A power engineer is analyzing a massive industrial system, something with huge motors using three-phase AC power.
Three-phase, so that means three different voltage waves all happening at once.
Precisely. Three waves, and they are all out of sync with each other. How does that engineer manage to visualize and combine them?
That sounds incredibly complicated.
Oh.
I mean, you can't just add three sine wave equations easily, can you? How can they possibly keep track of everything changing at once?
That's the perfect question. And that is exactly where the magic of phasors comes in. Phasors are basically the visual language of AC. For instance, in that three-phase system, engineers represent those signals using three simple arrows. Three phasors, perfectly spaced, 120 degrees apart.
Oh, so it makes load balancing immediately obvious just by looking at a picture.
It transforms the complexity of that continuous time variation into a simple geometric snapshot. Okay, let's unpack this core idea. A phasor is, at its heart, a clever substitute. Instead of tracking the voltage or current as it changes over time sinusoidally, we represent that entire oscillation as a single rotating arrow, or vector.
A single rotating arrow.
Yes. Think of our primary analogy here. A rotating searchlight. The fixed length of that light beam, the arrow, that represents the peak or amplitude, V naught or I naught.
Okay, so the length of the arrow tells us the maximum value of the signal.
Yeah.
And the speed of rotation. That must be fixed by the frequency, like 50 hertz in India, right?
Precisely. The speed is fixed at the angular velocity, omega. So, now here's the key mental image. If you stand to the side of that rotating searchlight, the vertical position of the light beam on a distant wall, it just oscillates up and down.
Oh, I see. So that oscillating vertical position, that's the projection onto the vertical axis. That's the instantaneous voltage or current, V of t, I of t, that we measure at that moment.
You've got it. And this entire tool, it exists to simplify circuit analysis. When components like resistors, inductors, and capacitors are combined, their voltages and currents are out of phase.
And adding those out-of-phase sine functions mathematically is very tedious. It requires a lot of trigonometry.
Tedious is an understatement. It requires calculus sometimes. But phasors, they turn that complex sinusoid addition into simple vector addition.
So it becomes geometry, not derivatives.
Exactly. It's the bridge between the time domain reality and frequency domain simplicity. Now let us see how insert defines this, as we must maintain the exam-safe wording. Can you please read the formal definition of the phasor and its role in AC analysis?
Yes, of course. Reading from the textbook, a phasor is a vector which rotates about the origin with angular speed. The vertical components of phasors V and I represent the sinusoidally varying quantities V and I. The magnitudes of phasors V and I represent the amplitudes or the peak values Vm and Im. But here's a doubt. It also says these are not vectors themselves, even though we use rotating vectors to represent them. How is that possible?
That's an excellent point, a really sharp observation. And you are right, they are scalar quantities. Voltage and current are scalars. But the amplitudes and phases of these harmonically varying scalars, they combine mathematically in the exact same way as the projections of rotating vectors.
So we're just using the vector method because it's familiar.
Because
Because we already know the rules for vector addition.
Exactly. It makes the whole process intuitive and visual. We are borrowing a tool from geometry because it perfectly maps onto the problem. Let's use a minimal worked example to show the power of this. It will make it crystal clear. Imagine we have two AC voltages. Both have a 100-volt amplitude. Let's say V1 has a phase of 0 degrees.
Okay, V1 is the reference.
And the second one, V2, is lagging by 90 degrees. So instead of a half page of trig identities to add them, we just draw two arrows.
Right, two perpendicular arrows, each of length 100.
Correct. Now, if you add these two perpendicular vectors geometrically, what's the resultant?
It's just the hypotenuse. So
Yeah.
square root of 100 squared plus 100 squared, that's 141.4 volts.
Instantly. And the phase angle.
It would be exactly 45 degrees lagging.
See, phasors immediately tell us the total voltage is V total equals 141.4 sine of omega t minus 45 degrees.
Wow. Geometry is so much simpler than time-domain algebra.
It really is. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now, this visual tool is essential for the rest of the unit. We already saw that in a pure resistor, voltage and current are in phase.
Their phasors point in the exact same direction.
Correct. But as we move to the next topics, we'll see that an inductor. It forces the current phasor to lag the voltage phasor by 90 degrees.
And a capacitor that must force the current phasor to lead the voltage phasor by 90 degrees.
Exactly. And phasors make these phase shifts so easy to visualize. It's the key to understanding LCR circuits. Okay. Now, this topic has three. Silent killers that often trip up students in exams. Let us address them now. Misconception number one. The wrong idea is that a phasor is just the sinusoid written in a different notation.
Students probably think this because they're representations of the same signal. No.
That's exactly why. But the correct concept is that the sinusoid is the movie. It's the time domain view, showing voltage changing every single instant. The phasor diagram, however, is a frozen snapshot. It's a frequency domain view, usually taken at t = 0.
So you lose the time information, but you gain the geometric simplicity.
Perfect. Which brings us to misconception number two. The wrong idea is that the angle of the phasor changes as time progresses in the diagram.
But we describe it as a rotating vector, which is why that's confusing.
It is confusing. The correct concept is that the angle shown in the phasor diagram, phi, that is the initial phase angle. It's fixed at t = 0. The diagram itself is a photograph, not a video. And that angle, phi, is used to establish the phase relationship between different components at that one instant.
Okay, so we fix the phase angle in the diagram, and the phasor method only works because we are analyzing signals that all have the exact same frequency, so their relative phase difference stays constant.
Absolutely correct. And that leads directly to the third killer point. Phasor diagrams are valid only for AC.
The relative phase angle between them would continuously change, and a fixed diagram would be meaningless.
You've got it. It would be a spinning, useless mess. All right, to ensure these concepts really stick, let's build some memory anchors. First, let's try a phrase. Phasors are the X-ray of AC.
The X-ray of AC. I like that.
Yes, because they show the hidden phase structure that the plane sine wave graph hides. Now for a physical anchor, try this. Extend your arm straight out. Now rotate it smoothly in a circle.
Great.
That's the sine wave movie. Now freeze your arm at one specific angle.
Freeze.
That freeze frame, that's the phasor. It captures the crucial phase angle, phi, and the amplitude, which is the length of your arm. To wrap up this deep dive, here are 3 exam-safe factual summary points about phasors. 1. A phasor is a rotating vector that represents a sinusoidal AC signal, with its length defined by the peak amplitude, Vm, and its rotation speed defined by the angular frequency, omega. 2. The instantaneous value of the AC quantity at any time t is given by the vertical projection of the rotating phasor onto the vertical axis. And 3. Phasor diagrams convert the difficult analytical addition of out-of-phase AC signals into simple vector addition, making the analysis of complex LCR circuits geometric and efficient. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Thank you for diving deep with us today. All the best for your studies.